Hi everyone, welcome back to the video series on data centers. I'm just going to be so the last day I finished here with connection orientated communication, and I'm just about to start here with the three-way handshake. Sounds pretty simple, but things don't always flow so smoothly. Sometimes during a transfer, congestion can occur because a high-speed computer is generating data traffic a lot faster than a network can handle. Transferring a bunch of computers simultaneously send datagrams through a single gateway or destination can also botch things up nicely. In the latter case, a gateway or destination can become congested even though no single source caused the problem. In either case, the problem is basically akin to a freeway bottleneck: too much traffic for too small a capacity. It's not usually one car that's a problem. There are simply too many cars on that freeway. Okay, so what happens when a machine receives a flood of datagrams too quickly for it to process? It stores them in a memory section called a buffer, but this buffering action can solve the problem only if the datagrams are small, are part of a small burst. If not, the datagram deluge continues. A device's memory will eventually be exhausted, its flood capacity will be exceeded, and it will react by discarding any additional data. In this, both the sending and receiving machines or workstations. This is not done in simple numbers, but in the amount of bytes that can be sent. Acknowledgments. Reliable data delivery ensures the integrity of a stream of data sent from one machine to another through a fully functional data link. It guarantees that the data won't be duplicated or lost. This is achieved through something called positive acknowledgement with retransmission, a technique that requires a receiving machine to communicate with the transmitting source by sending an acknowledgement message back to the sender. When it receives data, the sender documents each segment measured in bytes. It then sends and waits for this acknowledgement before sending the next segment round of bytes. When it sends a segment, the transmitting machine starts a timer and retransmits. If it expires before an acknowledgement is returned from the receiving end. In figure 212, the sending machine transmits segments 1, 2 and 3. The receiving node acknowledges it has received them by requesting segment 4 with an ACK4, which it receives. When it receives the acknowledgement, the sender then transmits segment 4, 5 and 6. If segment 5 doesn't make it to the destination, the receiving node acknowledges that event with a request for the segment to be resent. The sending machine will then resend the lost segment and wait for an acknowledgement, which it must receive in order to move on to the transmission of segment 7. The network layer. The network layer, also called layer 3, manages device addressing, tracks the location of devices on the network, and determines the best way to move data, which means that the network layer must transport traffic between devices that aren't locally attached. Routers layer 3 devices are specified at the network layer and provide the routing services within an internetwork. It happens like this. First, when a packet is received on a router interface, the destination IP address is checked. If the packet isn't destined for that particular router, it'll look up the destination network address in the routing table. Once the router chooses an exit interface, the packet will be sent to that interface to be framed and sent out on the local network. If the router can't find an entry for the packet's destination network in the routing table, the router drops a packet. Two types of packets are used at the network layer: data and route updates. Data packets used to transport user data throughout the internet, where protocols used to support data traffic are called routed protocols. Examples of routed protocols are IP and IP version 6. Route update packets used to update neighboring routers about the networks connected to all routers within the internetwork. Protocols that send route update packets are called routing protocols. Examples of some ones are RIP or RIP version 2, EIGRP and OSPF. Route update packets are used to help build and maintain routing tables on each router. The routing table used in a router includes the following information: network address, protocol specific network addresses. Our router must maintain a routing table for individual routed protocols because each router protocol keeps track of a network with a different addressing scheme: IP, IP version 6 and IPX, for example. Think of it as a street sign in each of the different languages spoken by residents that live on a particular street. So if they were American, Spanish, French folks on a street named Cat, the sign would read Cat, Gato, Chat. Interface. The exit interface a packet will take when destined for a specific network. Metric. The distance to the remote network. Different routing protocols use different ways of computing this distance, but for now no that some routing protocols, namely RIP, use something called a hop count, the number of routers a packet passes through en route to a remote network, while others use bandwidth, delay on the line, or even tick count 1/18 of a second. And as I mentioned earlier, routers break up broadcast domains, which means by default broadcasts aren't forwarded through a router. Do you remember why this is a good thing? Routers also break up collision domains, but you can also do that using layer 2 data link layer switches, because each interface in a router represents a separate network. It must be assigned unique network identification numbers, and each host on the network connected to that router must use the same network number. Figure 2.4 shows how a router works in an internetwork. Here are some points about routers that you should really commit to memory. Routers by default will not forward any broadcast or multicast packets. Routers use the logical address in a network layer header to determine the next hop router to forward the packet to. Routers can use access lists created by an administrator to control security on the type of packets that are allowed to enter or exit an interface. Routers can provide layer 2 bridging functions if needed, and can simultaneously route through the same device. Layer 3 devices. Routers in this case provide connections between virtual LANs, VLANs. Routers can provide quality of service, QoS, for specific types of network traffic. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.